Hello everyone, welcome to the series of Talks 21. My today's guest is Nassim Haramein. Nassim Haramein is a theoretical physicist, visionary thinker, and founder of the International Space Federation. For over 30 years, he has been exploring the fundamental nature of space, the connection between quantum physics and gravity, and the role of consciousness in the fabric of the universe. His unified field theory proposes that reality is fractal and holographic, suggesting that everything in the universe is deeply interconnected through space itself. His work offers a bold and interdisciplinary approach to advancing our scientific understanding and exploring new frontiers in energy, technology, and cosmology. Dear Nassim, thank you so much for coming to Talks Vietnam, and I am looking forward to talking about universe.
Oh, thank you. Thank you for having me. It's such an amazing place here. It's remarkable. Thank you so much.
We live in a beautiful space. Our Earth is also beautiful, but I can see what is happening, that we are coming to a point which I call singularity, social singularity.
Yeah.
Things are changing.
Yeah.
Things are changing in sociology, on our Earth, and the things are also changing in physics, in theoretical physics.
Yeah. I think we're arriving at a nexus in our evolution, and we have to transcend a very important moment right now. I think and everything is changing in science. It's been kind of stagnant in physics, in fundamental physics. It's been stagnant for almost 100 years. And so there's a big breakthrough that's about to happen, and it's very exciting.
That's so exciting. It's a breakthrough in physics, in science, and also in sociology. It's breakthrough in everywhere.
Right.
And from what I can say, the physicists, theoretical physicists towards the end of the 19th century, they were like the optimistic, then they will already explain all physics. There's a few points to be solved, and we will have unified theory.
Yeah, it was going to be done.
And then came Einstein. That was like a big shock.
Yes.
And then quantum theory, which put it a totally different level of existence.
Exactly, yeah. And it's remarkable because this repeated again, like in the early 90s, the general sense is that we had pretty well everything we needed. And, we were almost there in understanding the foundation of the universe and everything. And so there was a certain level of arrogance that we were good. There was no need for new theories and all this. And unified theory was not really a popular thing to be working on. I was often told, why do you want to unify quantum mechanics with general relativity? They both work in their own domain. We're happy with it. And my answer was always, because if you haven't noticed, big things are made out of small things. So there must be a way to connect these two theories. General relativity deals with the big things, and quantum mechanics with the small things, and they don't agree. So there must be a continuous relationship between the two.
And so now what we can say probably that the effects of quantum theory are working on the big scale as well. It's not
right. Yes, we've discovered throughout the years, and with better instruments of observation, and theories have been developed that show that quantum effects at the cosmological level have significant application, and that you can't just ignore quantum effect at the cosmological level. In my opinion, and from my work, you cannot ignore cosmological effect or general relativity at the quantum level.
It makes sense.
And that second part, that applying general relativity at the quantum level, is not well known. It's not popular. And, you have people like Roger Penrose that are insisting that actually we need to modify quantum mechanics instead of trying to geometrize instead of trying to quantize gravity. And so he's on that path, but, there's not many people either than Einstein and Rosen in 1935 that tried to geometrize quantum mechanics, that tried to apply general relativity, which is the geometry of space-time at the quantum level.
So, and you have made advances in that field. So, what can we expect? So, unified
Well,
theory is much closer now.
Yeah, I think so. Yeah, absolutely. I think it's almost there in the work I've been doing. And basically, I didn't really invent anything new. I just rearranged what was already there. And if you want the 1 second conclusion is that the nuclei of an atom is a mini black hole, is a mini singularity. And that's why it's extremely energetic and stable, and it is like a feature of space-time itself. And this is what Einstein and Rosen tried to do in 1935, but they didn't have the tools we have today. They were missing one tool.
Okay.
They were missing some of the data. Yukawa had just published papers, but these papers were not well understood, and there was no measurement of the nuclear force, the color force at the nuclear level. And so they didn't have that piece of information they needed when they tried to make the proton, the nuclei of the atom, a little black hole. That's what Einstein and Rosen, they made it. This is where wormhole mathematics come from that paper they wrote, right? They showed that space-time can wrap itself into like a wormhole tube, which is with ends in little black holes mouth of the entrance of the tube,
which are protons,
which they tried to make particles, like the end of the tube, like was particles in the theory they were writing. And but when they calculated for proton, the nuclei of the atom, when they calculated what would be the size of the wormhole tube for the proton, so they put the mass of the proton in there, they got a radius that was like 10 to the minus 54
way below
52 meters, minus 50,
Planck constant,
it was like way past the Planck scale. Like, so the Planck scale, for the viewers, is the smallest scale. When you put all the constants of physics together, this is the smallest like pixel of space-time.
Yes.
And so they were like, oh, it makes no sense. And nobody noticed. And this is the error. Like, I was the first one to notice, really. Nobody noticed that the radius they got relative to the radius of the proton we measure is exactly alpha g. Not approximately, it's like exact. And alpha g is the constant that relates the strong force with the gravitational force. It's the ratio, like how weak is the gravitational force relative to the strong force, which is the force that holds the nuclei together in the atom.
And they already had this, so they didn't have this information at that time. That will be found later, but nobody noticed this ratio.
Yeah, nobody went back and went, oh, wow, they had found the ratio between the strong force and the gravitational force.
It's not by coincidence.
Yeah. And so if you notice that, then it's like a no-brainer. Einstein would have found it, right?
Yeah,
like he would have totally found it, but they didn't have it. And so, because then what you do is you just reverse the equation. Instead of saying how small the radius of the proton would be if it was a black hole, you say how much energy do I have to put in the size of the proton we measure for it to be a black hole. And the energy you put in is exactly the energy you need to produce the strong force. So then all of a sudden it all comes together and you realize that the nuclear force, the strong force, which we utilize, right, in nuclear fission, nuclear power, all this, we're extracting the strong force from the atom, right? And so then they would have realized actually that force is the force of a mini black hole we call the proton.
This is absolutely fascinating. So this is a breakthrough in physics,
Yeah,
which is
totally.
current. It's
Yeah, because all of a sudden you're applying Einstein field equations to the atomic level, and you're getting the right answers, right? All of a sudden links, and you know, there's caveat to this, meaning that when you get this right answer, then you realize that that ratio between the strong force and the gravitational force is not just in the way I just said it, but actually it's actually a ratio that's present in between the Planck scale and the proton as well. And so you see that the Planck scale is related to the proton, because the next thing you're going to ask when you write this equation is, where is the energy coming? You know, to make the proton a black hole. Like, okay, you have the energy to make the strong force. It's curving space-time, but where is the energy coming? And then when you arrive at the Planck, you see that the ratio is telling you it's the Planck scale that's providing the energy. And now you arrive at something that quantum mechanics found at the very beginning of quantum mechanics. Max Planck found that an oscillator has almost an infinite amount of energy, even at 0 Kelvin.
Right, it's a 0 point energy.
0 point energy. And that energy renormalizes at the Planck scale. So it's like, I call it a Planck plasma. And it has to do with the structure of space-time itself. See, because general relativity tells us that space-time curves to produce forces, but it doesn't say what space-time is. What is that? Right? Okay, it's conceptual. But, okay, it's conceptual, yes, but it's producing a real force. So there's something, you know, it says that space-time curves around an object to produce the force, right? Like the typical analogy is they put a ball on a trampoline on a, you know, flexible surface, and then they put another ball that's orbiting. You know, and it's being attracted to the big ball because the surface
it goes down.
It's called curvature, right? But I don't like that analogy. It's not a good analogy. There's a better analogy, is you in the bathtub, right? So if you're in the bathtub and you have a rubber ducky, you have rubber duckies here, you know, like a little, you know, toy.
Okay.
That floats.
Right,
you know?
The
rubber ducky. And you pull the plug. You get like this vortex.
The vortex,
And then put the rubber ducky there, and it orbits, right? And it's attracted to the plug. Well, what Einstein general relativity does is that it looks at the surface of the water and it's curving, right? So conceptually, you can describe the curvature, right, as what's attracting the rubber ducky.
Yes.
But what is really happening is that the water that looks smooth like this, curving, right? When you look close, you see that the water is made out of grains, right? Atoms, like molecules, right? So there's hydrogen and oxygen, and it's the collective behavior of all these molecules together that is making the appearance of curvature. So in space, curved space-time, why is it curving? Because space itself has a dynamic, a fluid dynamic, which is the 0 point energy that is producing quantum vacuum fluctuations. It's like space is full of electromagnetic fluctuation. And maybe I should give a history on 0 point energy so the viewers understand better. But this is the general idea, is that space between us, space between atoms, space inside the atom is full of energy. It's full of electromagnetic fluctuation. And they're chaotic everywhere, but they actually, you know, in region, they organize, like when you pull the plug in the tub, they organize and it curves space-time and makes a particle that we see. It makes the material world. So basically you don't have material world and space, you just have space that goes into densities that looks like the material world.
Okay.
Yeah.
It's amazing. So at 0 Kelvin, we have huge potential of energy that we can explore. So
That's right.
And
And you know, when Max Planck found this, so Max Planck wrote the first equations for quantum mechanics, right?
yes.
He was trying to solve a problem in classical physics at the time that had to do with thermodynamics of an object called the black body radiation problem, right? So basically, he was trying to make a better light bulb, by the way, right? And so he was looking at like the filament of a light bulb, and when it heats, what frequency it emits. So at what temperature, the graph is like what temperature, what frequency comes out, right? Like, so as it gets hotter, it goes towards the blue and then ultraviolet and so on. It gets higher in frequency, right? Well, the equations of the time said that as you went up in temperature at like 5,000 Kelvin, all of a sudden the ultraviolet should go infinitely emission of ultraviolet. Like the body that's radiating should be radiating infinite amount of energy. And so that's not what we were measuring in laboratories. So he tried to solve the equation and he didn't know how to do it. So he just said, okay, well, if I stick this constant in there, which became Planck's constant, he called it H, became H bar. If I stick that in the equation, so he's describing a little oscillator. You got to understand at the time, like atoms were, this is 1900. So like at the time, atoms were just starting to be understood and like, you know, so they were describing it as like a little oscillator. Yeah. And in quantum mechanics, when you learn quantum mechanics in school, they tell you the oscillator is like a spring with a weight on the end that's oscillating, right? But that's not a good analogy neither. Right? It's better to think of like something spinning. It's equivalent mathematics, but spring and weights are not what the universe is doing.
Okay. Yeah.
What the universe is doing is a little oscillator that's spinning. And so he was describing that. And what it was saying is when he added this constant in there is that the oscillator was absorbing packets and emitting packets of electromagnetic fields. So that the electromagnetic field that's radiating from an object is not actually continuous, it's like in packets, so, which they called quantas. And then so quantum mechanics, right? Einstein eventually took the packets and made them and called them photons, and won the Nobel Prize for the photoelectric effect, and so but Planck was not happy with this. He thought this is bullshit. Like he didn't like his equation, right? And so he was like, well, maybe I can at least make the absorption classical and the emission in packets. And so by 1912, he wrote a generalization of his first law. And he was able to get the same result as his first law, but with the energy that's absorbed being continuous, not in packet. He was trying to make it more classical. But the thing is that when he did that, he dug into the equation a little more, and when he was calculating the energy inside the little oscillator, the internal energy, there was this term that kept on coming out, like that he couldn't get rid of. And so 1.5 H bar mu came out, and it was like a part that said something really strange, right?
0 point energy.
Yeah, and he called it that way because it was saying that at 0 Kelvin, where the oscillator should be like frozen, like nothing happens, nobody moves, like more frozen than Alaska, yeah, like,
of course, 0 Kelvin.
0 Kelvin. No. Well, when it was supposed to stop thermal emission, it shouldn't oscillate anymore. It should be done. the equation was saying there's actually infinite amount of oscillation internally to the oscillator. And that, you know, was weird. And like, so then Einstein worked on it, Stern worked on it, but there was like a way, like in one way, the tendency was to try to get rid of this, right?
All right.
Instead of going, wow, we found the source of existence. Right?
Which is the 0 point energy.
Right. Which is the fact that an oscillator has a continuous source of energy. Instead of thinking that way, they were trying to figure out a way to like get rid of it. Right? In some ways. And basically, so basically that's the state of affair that it was left in for all these years. I mean, there's complexity, but basically all these years, basically what they did is they said, okay, well, we're going to assume that all the modes of oscillation of the 0 point energy cancel out, right? Because there's infinite modes, so they cancel all out and it's zero. And so you put the equation to zero and you're good, right? Except that when you write the equation rigorously, if you do that, that means your oscillator is now a magical object, right? It has oscillation, but it doesn't have a source of energy to oscillate it. So if you calculate the self-interaction of the oscillator, it would like dampen very quickly. And within seconds,
all would be frozen.
Yeah, everything would go away, right? Like after the Big Bang, within billionth of a second, right? Everything would have vanished, run out of energy and vanished. And so this is a problem that's not addressed, right? It makes, not to get too technical, but basically, you know, it makes the equation commutative and the equations have to stay non-commutative, right? So commutative means like that it doesn't matter the order.
You can switch.
But non-commutative matters the order. You can't. So basically, the source of energy has to be there for the oscillator. So not to get lost in details, but basically, I showed that actually. So one of the issues in 0 point energy is that if there's all this energy in the space, why is it not curving space-time? You know, if you calculate the amount of energy that 0 point energy would have in the space, even so you say, okay, it's not infinite, it stops at the Planck scale, right? At the Planck scale, that's the maximum, right? You still have 10 to the 93 grams per centimeter cube of energy in the space. It's super high
10 to the 93 per centimeter cube is a 0 point energy.
Yeah,
okay.
in the space. It's crazy.
Yeah, that's crazy.
It's like 10 to the 113 joules per centimeter. I mean, it's like insane, right? It's an amount of and so you go, but you know, that should curve space into a point, right? And basically what we showed is that it does.
And so from here comes the theory of interconnection of the holographic universe.
Exactly, meaning that the curve, you have to consider, and so Wheeler kind of tried to consider what the 0 point energy would do. And he showed that, like, because you can't just do the equations of 0 point energy and the equation of general relativity over there and not put them together and say, what is all this energy going to do to space-time? And when you do that, you end up with like space-time is like granular because the energy is curving space-time into, you know, little bubbles. So he called it quantum foam. And the little bubbles are at the Planck scale.
Yes.
Right? And so basically the structure of space-time is fluctuating with these bubbles at the Planck scale. So then I calculated, okay, so at the proton scale, what is the residual energy right? Because from the Planck scale to the proton scale is a huge scale difference, like 20 orders of magnitude.
Yeah.
So if you take, I'm sorry, I'm just giving you the whole history.
This is great. I think it's very important because it's so consistent and one can understand what's really happening. And
Right.
I understand, but it might look a little involved, but I think this is so important because we are talking about breakthroughs in physics here now.
Yeah,
It's
exactly.
absolutely
An
fascinating.
understanding of reality.
Yeah.
Yeah. So if you look at there's 20 orders of magnitude difference, right?
Between Planck scale and proton
In proton scale. So
Yeah.
it's like huge. So if I grew a Planck so that it was the size of a grain of sand, right? The proton would be from here to Alpha Centauri big, right? Like
20.
40 trillion kilometer diameter, right? So imagine how many grains of sand you can put in a proton that's the size of from here to Alpha Centauri, right? So the grains are really small, right? So we calculated, okay, so assume, let's make proper mathematics and not just assume that they all cancel out, the little bubbles, right?
Yes, and why should they?
Yeah. So then we take the proton, we say, okay, this is a cavity. How many of these little bubbles are in there? How many modes of oscillation, right? It's going to end at the size of the proton, the modes of oscillation, right? And it's going to go all the way down to the Planck, right? And so you can use equations that are called correlation function equations to figure out how many modes are going to be constructive and make energy that you can measure, and how many modes are going to cancel out. And so when you do those equations, it's remarkable. Because you get exactly the mass of the proton.
This is absolutely fascinating.
Yeah.
So this is a direct proof of the theory, right? Because otherwise, how could you, out of sample, get such a result?
Yeah,
which is
no
precise.
way.
There's no way.
There's no way.
Yeah.
And it's exact.
Yeah.
It's exact. It's like crazy exact. And then so now you can prove that actually it's 0 point energy that's producing the energy that we call mass, right? Because the proton is the mass, the atom, and all the atoms are proton mass, right? And so and you can do the same for the electron. I haven't published that yet, but it's the same. And so you can show that the material world is actually just a dynamic function of 0 point...
Of the tiny bubbles, which are 10 to 20 in one proton.
Yeah, exactly. And so now you see something completely different picture.
Absolutely.
So like objects are not separate. They're just flow of this dynamics. And that this constant...
And it's all discrete.
And it's all discrete. Exactly. And the discreteness is attached to space-time, meaning space-time is what's producing the discreteness because it's pinching, right? It's curving enough that it pinches and makes bubbles, right? So the two theories are no longer separate.
Yes.
And then, so when you apply Einstein's equation to the proton in this fashion, and you consider then, so the oscillator is no longer without a source of energy. It's constantly getting a source of energy. You see, the 0 point energy. And so when you so then you come from the other side. You apply Einstein's equation to the little oscillator, the proton, and then you find that it's a little black hole, right? Because of all the energy of the Planck's oscillators in there, because you're considering the two, right? So now it's a little black hole. So then you go, how much radiation, it's called Hawking radiation, the little black hole the size of the proton would give, right? Because now you have a mass much larger than the mass we measure for the proton, right? Because
of course, because it's a 0 point there.
Energy, and because most of the mass that you're measuring, you're calling it the strong force, right? That's why it's equivalent with the alpha G constant, right?
I see. Okay.
You are measuring the mass of the black hole. It's just you're seeing it as a force, right? Because when we measure a black hole in the universe, how do we measure it? we see the force it acts on the
yes,
other
right.
objects.
We measure the force. Of
Yeah,
course, yeah.
exactly. So it's the same thing. You're measuring the force of a black hole, and then you calculate the Hawking radiation of that black hole. I'm not trying to bore you.
No, this is fascinating.
Okay, and so you get this radiation that's called Hawking radiation.
Yes, yes.
So Hawking figured out that at the event horizon of a black hole, the little bubbles of space-time, the Planck scale bubbles, some of them would fall in. So they come up in pairs. They usually cancel out. But if one falls in, then the other one is radiated.
Yes,
it's
called radiation of black hole.
Yeah, exactly. Hawking radiation.
Hawking radiation. Yeah.
So if you have a little black hole, and it's true that you have a little black hole as a proton, then when you calculate the Hawking radiation, it better give you something correct.
Yes, yes.
Right? And so we calculated that, and sure enough, you get exactly the rest mass of the proton when you calculate the Hawking radiation that you're seeing from the outside. So now you've got two rest masses. You've got one you calculated inside from the modes of oscillation, and one that you're calculating radiating. So you have an exact relationship between what is being given by the 0-point energy inside the oscillator and what's being radiated. So the oscillator doesn't lose energy. It's constantly, getting the energy that it's radiating. So it's hyper stable. And this is what we see, when we look at the nuclei of the atom, the proton, not the nuclei as a whole, because that decays, but the proton themselves, they never decay. Never decay. We have never seen a proton lose energy, right? That's what I mean by decay, right? And all the theories says, it would be like trillions of times longer than the time of the universe before it would start decaying. So then we can calculate that in our equation, and we show it's way longer than the universe. But that's assuming that it's not getting energy from the amount of energy in the vacuum energy. We can say that it's going to be stable for almost to infinity, but I think it's going to be infinitely stable because it's constantly getting replenished by vacuum energy. And the stuff that's radiating, it's going in vacuum energy too, right? It's going into the space, which is vacuum energy, so you can have like feedback. And so that's when you start to get fractals, fractal effects when you have feedback in a system, and you get holographic principles, and all this comes out. Yep.
So our space is this huge number of bubbles, which are discrete. And there's a time scale, how it's interacting and changing.
Yeah, exactly.
Also relates to the Planck constant of time.
Yeah, exactly. It's related to the Planck constant. And because the Planck constant, which is h, was eventually found that like h is always associated with 2 pi. With 2 pi is like the
radius.
The circumference.
Circumference.
Yeah. So eventually it became h bar. Which
normalized
is
by 2 pi.
Yeah, normalized by 2 pi, exactly. And so it's called a quantum of action of angular momentum. So basically, you get this. It's like conservation of angular momentum. So you imagine like all the little Plancks, bubbles, if like the amount of them that aligns, right, then gives the spin to the particle. And then the amount of particles that aligns give the spin to the larger objects, and so on and so on and so on. And there's an experiment that supports that. It's called the Einstein-de Haas experiment. And it's basically you put a metal tube or a metal rod into a solenoid, into a coil, and you turn on the coil, and nothing should happen because the rod is in the middle. There's no differential field, so it shouldn't do anything. But the rod starts turning. And it's because you're aligning all the electrons which is like billions and trillions of electrons. So they're much smaller than the rod, right? But you're aligning them, and so all their angular momentum conserve into the rod and makes the rod spin. And so it's a good example of how this is like going through the scales, you know, how you...
So we are getting from the smallest scale to the biggest one, it's step by step, right? In that sense, we are like the atoms of one being and then the earth and stuff. So we can continue ad infinitum towards it, and then we can have cosmos of cosmos, etc.
Yeah, exactly.
So,
exactly. So you can imagine like fractal universes to infinitely big.
Yeah.
And you know, you can go
inside
infinitely small. The Planck scale is just one of the levels that defines the speed of light. But there's sub-Planckian, hyper-Planckian, or trans-Planckian size. And so because now we understand the scaling in our equations, now we can predict what the sub-Planckian size would be.
Indeed.
And how fast the speed of light is at that sub-Planckian size.
And the scaling works in the macro level as well.
That's right.
It is, so in that way we have like the wormhole of universes.
Yeah, exactly. Which is what Einstein and Rosen had envisioned.
Oh, okay.
Yeah, that it was like, you know, this black hole wormhole structure from infinitely big to infinitely small.
I believe this is actually a good point because many people talk about parallel universes, but they imagine there are infinite or huge, unlimited number of universes existing together.
Yeah.
But this is different. I think this is a totally different
more integrated.
More integrated as this
it's concentric instead of parallel. Yeah, because there's nothing parallel in the universe. There's always curvature. Parallel is... Minkowski space is actually, you know, it's a generalization, like an approximation that you say, okay, I'm only going to consider the objects I'm looking at, and I'm going to assume the rest of the space is flat. Right?
Yeah, that's a big assumption.
It's like, okay, well, you've removed everything else in the universe, so how good is going to be your calculation, you know?
It might be interesting intellectual concept, but in fact, this is what we have been doing in physics, right? We take the assumption that there is an observer, and which can look and analyze something that's separated from everything else. Which this showed is not the case.
It's not the case.
Yeah, so this is another very interesting thing that
and it leads to confusion. You know, a lot of confusion. Even in like really simple assumptions that like every physicist repeats as if it was a dogma, right? That there is no perpetual motion, and that there is no, you know, like you can't get more out of a system than what you put in, right? And things like that, which, you know, everybody repeats this. Students, everybody, physics, you know, if you say something different, it's like, oh my God, you don't understand physics clearly because you think there's perpetual motion. But then if I go to a physicist, like the top in the world, anybody, okay, and you ask, okay, so show me something that's not perpetual. Just show, like, point at something that's not perpetual. You can't, because everything is made out of protons, and protons seem to be like perpetually doing their thing, right? Like stars keep spinning, you know, even when a star explodes, what you see it doesn't just disappear. What you see in the middle is a black hole, right? And it's lots of energy, or a pulsar, but lots of energy. It's not like the star is gone. It's just that you're seeing the core. And so basically, you know, this idea that there's lack of energy, or you see, the problem comes from the concept of entropy, which is not actually well defined in physics, right? The principle of entropy. Because entropy is true, but only locally. It's always conserved globally, meaning that, how do I explain this? Right? Like, if you
if you don't do anything, the things tend to fall apart in a natural way.
Yeah, if you don't
right?
keep putting
And
energy in it.
that's on the macro scale.
Yeah, so
And it is assumed that the same should be happening everywhere.
everywhere.
Yeah.
But when you look at nature, so it's, if that's true, so you should be able to like to say, but where is the source of neg entropy, or where's the source of low entropy, right? So
Creation, let's say.
yeah,
What
like,
we can-
yeah. So because if there's entropy, if everything is going towards further and further disorder, right? There's entropy equations. Where's the source of order? So in the universe, if you look for the source of order, if you were like try to identify a source of order, what would it be? It would be gravity, right? Because gravity brings everything together and creates order from which disorder radiates from, right? Like gravity brought our sun together, right?
Yes.
And then the sun radiates, right? And we get the benefit, which is low entropy for us. And then we transform that low entropy into higher entropy, and the result is all the biology and everything we see, right? But when you calculate this, you would say, so then we must be absorbing heat from the sun. But that's not true. If we were absorbing heat from the sun, the earth would be burning by now, right? It has to radiate the amount of heat it gets. It has to radiate it back out equally.
Yes.
So what we get that produces all this is actually low entropy. It's actually order. Do you see what I mean? So then you say, okay, well, if the sun got that order and is radiating it to us, where did it get it from? Well, it got it from the galaxy. And then where did the galaxy get it? Well, the galaxy got it from the cluster and the supercluster and and eventually you get back to the Big Bang.
Yeah.
And then that's when you realize that, oh, okay, so then where did the Big Bang get it? Right? Right?
Yeah.
And this is where you actually, when you get to the Big Bang, you get back to the Planck scale. Right?
Indeed.
Yeah, and because I mean the Big Bang
Was from the point, one of those tiny points.
Yeah, one of those Planck scale point. And then you get that this is like the source of energy, right? That's the source of energy that feeds everything, but not just like one moment in time where it blew up into the universe, but that it's constantly happening. It's constantly feeding the thing so that it's constantly, so the Big Bang was like the result of an earlier bang, which is another bang, it's like constantly.
That's the sequence of the universe.
Yeah. It's not like one bang. It's not.
Absolutely.
Yeah. So then you start to see, oh, okay, so there's a continuous source of energy that's keeping everything going. And it's just being transferred from the Planck scale up the scales and then back down the scales and so on in the continuous feedback. When you wrote these equations, eventually you realize, okay, there's a direct relationship feedback between the electromagnetic field, what is radiated, and the gravitational field, what's going back in. And basically it's just the fluid dynamics, two movements of like the Planck scale is moving out, we call it electromagnetic. When it's moving in, we call it gravitational.
Fantastic. So in principle, the original proton, not proton, the tiny platinum particle made Big Bang, made our universe.
Yeah.
So it is in there. And what you are also saying that we are in the holographic universe, that like in each tiny proton we have the whole information.
Yeah, because this is crazy. It's crazy. Because when you calculate inside the cavity of the proton how much 0-point energy is in there, like how much fluctuate, like the whole thing, right? Not just the constructive waves that are putting the mass of the proton, but the whole thing, how much is in there, you get exactly the critical density of the universe. You get exactly not only the mass of all the other protons in the universe in terms of energy, but you get exactly dark matter and dark energy, like everything. Like,
by the way, this is also explained. We don't have any issue with dark matter and dark energy
that's
anymore.
right. Exactly. Then it all comes out. Then you realize, oh, it's just because we didn't consider the 0-point energy in the universe. So then, of course, we're missing 96% the mass of the universe because we didn't consider the 0-point energy. And so when you do that, then all of a sudden, everything, all the calculation comes out. But the crazy part is that you're studying a little teeny proton, right? I mean, there's more protons in your body than stars in the universe, right? But like, so you're studying a teeny proton and you get to understand the universe. You get to understand the mass of the universe. And when you actually do the math, you get the right mass, you get the right temperature, you get the right size, you get everything about the universe by studying one proton.
Yeah, it's the recursion. It's incredible recursion of universes.
Yeah.
So what they said, that the smallest one and the biggest one, it's in a circle. I believe we can imagine.
Right. The snake that bites its tail.
Yeah. That bites its tail. That's
Yeah. So like, there's so many ancient civilizations that talk about this. And you know, I had the honor to like go and meet with the Dalai Lama in Dharamsala, and you know, I was talking, and you should have seen his eyes, you know, light up. You know, when I was telling him this, he goes, "Oh, but this is in our Buddhist tradition," and da, 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 da. And I was like, and I was supposed to only have, you know, our group was supposed to only have like 20 minutes with him. And so he turned around and he did something. He talked to his lamas, and I didn't understand, of course. And I thought maybe I said the wrong thing. Maybe he's upset with me. And when he had said to his lamas, cancel all my other appointments, and we spent like 4 hours together. It was so awesome. And so it's there in many ancient civilizations, like the idea that the small and the big are connected, and that you can't, you know, that like everything is interconnected, and that's how everything becomes what it is. And so,
and from here, of course, we can ask, so what is the purpose of our being? What does it imply, all this information? But even before that, there are crucial physical consequences, right? You are talking about the theory of controlling gravity. So how should this work?
Because now you get a different view of gravity, because all of a sudden, so when you write these equations, so in the paper we're in peer review right now, we show that like you can take these equations, and then so now you can plot, you use Einstein field equation, you solve the metric, and you see that the color force, which is the force inside the proton that we measure now, we measure the force inside the proton. The equation gives the exact correct answer, and then we can show that force. So it starts at the Planck force, becomes the color force, it becomes the residual strong force. That's the force outside the proton that keeps the other protons in the nuclei. And then you can follow the force, and each time it goes through a phase transition, which is called a Yukawa potential, and then it becomes the gravitational force. So you can see that actually the gravitational force is super weak, that we, you know, like that we experience today, you know, is actually the source of it is actually the Planck force.
Yes. Okay.
That all the forces is the Planck force, right? It's the Planck field. And so now the Planck field is an electromagnetic field. So now you have a direct path of engineering how to produce force. You see? So now, like with electromagnetic fields and like plasmas and all this, you should be able to create enough, like you can align the Planck scale. So like the Planck scale is chaotic here, right? Where it's not a proton, when it's not an atom, right? Well, if if you create enough of an electromagnetic field in the right configuration, you can organize the plant so you make like a big atom or a small star in laboratory, and now you have control over gravity. You can curve space-time.
I see.
You can control how...
Systematically, you can, by curving all different spaces, you can beat the gravity, or you can change the gravity for a mass object.
Yeah, exactly. You can make a local gravitational bubble, right? An artificial local gravitational bubble. And if you do that, then you have like a spaceship engine, like you have a warp drive.
So what we see in sci-fi is actually coming to
it's coming. Yeah, it's remarkable. But you know, if you look at sci-fi throughout history, it's always ahead.
Yeah, of course.
Yeah,
which is another mysterious thing. How the information somehow propagates.
Right.
That would be another topic.
Yeah. It's another topic, but it's true. Like it's always ahead. Like cell phones, you know, refrigerators, like you know, submarines.
Artificial intelligence.
Artificial intelligence. All this is all in sci-fi before we come up with it, right? So warp drives is coming.
So this is okay. So once we manage to control gravity like that, yes, we can have flying objects and stuff. That's one thing. And then another thing, what about traveling through space, like beating the speed of light. Let's say.
Yeah. Well, that would be the step after, but you could definitely, you know, by controlling gravity, even if you're doing a half decent job at it, you should be able to like go to Jupiter in a few minutes. Yeah. Right? So this is already like remarkable. You can go orbit Jupiter for the weekend, you know, and come back for...
And we believe in our lives this should happen, I believe, right? We are very close now.
Yeah, we're very close. And so, you know, and people might think, wow, that's crazy. That's bizarre. What is he saying? But, you know, if you went to like the village where the Wright brothers lived, you know, like 2 weeks before they flew the first plane, and you said, in 2 weeks, we're going to take, you know...
This thing?
Yeah, like this huge thing that's like hundreds, thousands of pounds or kilos, of material, like engines and, you know, the wood and all the people on it. And we're going to lift it up in the air just by pushing wings against everybody would have said, you're nuts. Those guys, they make bicycles. They're not going to make a thing that flies. And so it's just but then they flew the plane, and you know there was hundreds of papers published.
Before that, it's not possible, right?
That's impossible.
Proving rigorously that flying material is not possible.
It's impossible.
And they didn't, fortunately, they didn't know about this, so they could construct a plane.
Right, exactly. The Wright brothers, they were just bicycle makers. They're like, yeah, let's make a plane. And so basically, you know, the physicists hadn't noticed that, you know, birds and
which is crazy, right? that I don't understand. But this is actually similar. People tend to be blind to some obvious things, right? Why would birds be flying? Why couldn't we construct an airplane? And still they were trying to rigorously prove it. Yeah, which is very curious to me.
And actually for years in Europe, they continued to publish papers saying that the plane was impossible and was a hoax, right?
Okay.
And so basically, you know, it's the same. You know, the fact that everything is actually perpetual and that we keep insisting
that nothing can be perpetual.
Nothing can be perpetual is like missing the birds flying overhead and going, nothing heavier than the air can fly. And it's like, what about the bird over there, right? And then, so basically, you know, we're in that place. And then all of a sudden, so we're in that place before the Wright brothers, where if you talk to people about like, oh, you could you could just curve space-time. You don't need a rocket with like, millions of pounds of fuel in it. Like you can actually curve space-time locally and fly.
And
then people go,
maybe we should
are you crazy?
stress that there will be no acceleration, right? Once we curve the space side, how will it feel?
How do you get the acceleration? Yeah. Well, the acceleration comes because when you're controlling space-time, you're curving space-time bubble. So think about the vortex you're making in space. You can displace the vortex, right? Because you're controlling the spin of the electromagnetic field, so you can move it. So imagine you made a little singularity and it's making a huge vortex around your ship, right? And now you displace, by controlling the spin, you're displacing the singularity up a little bit. That means that you're creating more curvature above and less below.
Yeah.
So now the thing is falling.
Towards the curvature, like water going through it.
Exactly.
Yes.
So you're falling through a wormhole ahead of your ship.
Amazing. And and what is the theoretical speed of that?
Yeah, so you should be able to accelerate to the speed of light within seconds, like less than a second. If you do it like significantly, I mean, there's whole kinds of like material, development that has to happen before that happens, and all
so
this.
It doesn't break.
So we'll stay below speed of light for a little while.
Let's make the 21% of the speed of light for now.
That would be. That gets you from New York to here within seconds. So that's good enough.
That's good enough.
Yeah, so no jet lags anymore. That's already nice. But what would happen? So this is another misconception, is that when you take the Lorentz invariant, so you take special relativity, or the Lorentz contraction, right?
Yeah, of time. So I wanted to ask, how will that be with time and aging if you make this?
So basically, that the mass would go to infinity when you arrive at the speed of light, right? That's special relativity.
Yeah.
And that's because you're considering spatial relativity in flat space. You're not considering the gravitational field, because that's how it was written. Einstein wrote it in flat space and then came up with general relativity. And so the tendency is for physicists to always keep these two in some ways separate, although they're connected. It's actually a wrong answer to say that at the speed of light, the mass would go to infinity. What it should say is that at the speed of light, everything should go to the Planck scale. Right? So basically, everything would like pinch back to the Planck scale. And so you become the vacuum. You become, and since the vacuum is holographic, now you can reconstitute. I don't say, I have that figured out, how you do the reconstitution on the other side, okay?
Okay.
I am working on that part.
Okay.
I'm happy with a small percentage of the speed of light for now. But, on the other side, theoretically,
so theoretically you can go arbitrarily close to the Planck scale, meaning that you slow time, so then you could accelerate the speed of light.
So then you wormhole through the Planck scale wormholes. To where you want to go, and then you come out on the other side, and you're there.
Okay.
And so you could cross a galaxy within, billionth of a second, right? And then I calculated. I have the calculation. So how long it would take you to go across the universe?
Okay.
And
how long?
It would take 10 to the minus 23 seconds to go across the universe. It's the refresh rate of the universe.
Okay.
And that's exactly the time it takes a proton to do one turn at the speed of light. It's remarkable, huh?
That's remarkable.
Yeah, it's remarkable. I was blown away when
this connection, is there like a theoretical reason for that? Why it should be the one spin?
Well, it came out naturally from the equation. I was trying to calculate, okay, so if the Planck scale has like what makes the Planck scale? Like if the Planck scale makes everything else, what's making the Planck scale? So it was sub-Planckian, right? So like
the Planck scale in Planck scale, right? We have this infinite recursion.
Yeah, exactly. So the sub-Planckian scale or trans-Planckian. And so then I calculated this because now I know how it's scaling, right? I know the scaling factors because my equations naturally show that.
And the scaling factor stays the same.
I'm assuming that.
Okay.
I'm assuming that. And but I mean, in order for the Planck scale to have its mass and its energy and its radius and all this, then the Planckian scale would have to be that value I've found, right? Like otherwise everything would break down. So I'm pretty confident it's correct. And so then I calculated, okay, at that scale, what would be the speed? So then I get a speed 10 to the 40th time faster than light. Okay? It's crazy.
That's crazy.
And that's the relationship between the proton and the universe, and so that makes the proton the center, but the Planck scale the center. But basically, what happens is that so then I said, okay, so if the mouth of the wormhole at the Planck scale is the Planck scale, then the information cannot be Planck scale; it has to be sub-Planckian. So then I calculated if the sub-Planckian scale sent a bit of information through the Planck scale across the universe. So it went from one side of the universe to the other side of the universe through all the protons. It went through all the protons and then onto the other side of the universe. I got the exact value of the time it takes one proton to make a turn. So basically, it's like gears within gears within gears, you see?
I see. So this one turn of the proton is the time when it refreshes, updates.
Yeah, on the universe. The universe is refreshed. Every time a proton makes a turn, the whole universe is refreshed so that the whole thing continuously work together. Like everything knows where everything is. Like everything is in connection.
Total connection.
Yeah, it's remarkable.
So the physics here is modern, real. New physics is now proving the interconnection of our existence.
Yeah, there's more and more evidence. And then it explains as well entanglement, because we do see the connection. We can see that particles can be connected at a distance, no matter how far away.
Information is, this, by the way, just for me, the quantum entanglement, it was a clear total violation of the physics before. That was just totally inconsistent internally, right?
right, exactly. So. And when Einstein wrote those papers, he was trying to make fun of quantum mechanics. He was showing, this is not possible. So clearly quantum mechanics is wrong. And then we started to be able to measure it. So in some ways he was right, saying it was wrong, in quantum mechanics, because it's actually not quantum mechanics that does that. It's because there's micro wormholes, which is general relativity. So he was right to say it was wrong.
What is the essence? Even a microscope, this is amazing.
It's amazing. And he wrote these papers on entanglement a few months apart from the paper on wormholes. For the proton, for the particles, but he didn't put the two together. I know, crazy.
That's funny.
Yeah.
So they were actually very close.
They're very close, and now it's put together, but it's very it's a conjuncture. It's called ER equals EPR, right? So because ER is Rosen and Einstein that wrote the paper on the wormholes for particles. And then EPR is Rosen, Podolsky, and Einstein, which wrote the paper on on entanglement. And so the two together,
it's the same.
yeah, and so they put ER equals EPR. So it's some of the best physicists on the planet that came up, Medicina and Sudskin and others that came up with this, but they don't have a formal connection, and I do, like these equations lead to that. Yeah.
Wow,
Yeah, it's exciting.
This is so exciting.
Yeah.
So now we are having singularity in physics. We are having singularity in our Earth in sociology.
Yeah.
Let's hope that we are conscious enough not to destroy all these beautiful things that we are finding out now.
Yeah. I mean, it leads to consciousness as well,
yeah,
you know,
yeah.
and we're going to have another talk about it.
Yeah, that would be amazing. I would love to invite you for another talk about consciousness. Maybe towards the, maybe what is for you, what would be the implication for our thinking, for our living, to strive for, maybe in just few sentences, that we make another talk for that in the future. I would like to thank you so much for this deep explanation. I believe it was enlightening for the viewers, similar as for me. It's absolutely amazing. We are getting to the edges of our knowledge. And what do we imply now for our lives? How do we handle this knowledge? How do we make sure, or maybe perhaps not make sure, and try our best not to destroy ourselves, to make use of this knowledge?
Yeah, I think it's really important that, like, you know, this knowledge is, I think humanity is ready for it. Any knowledge can be used for all kinds of purposes. I think we have a really amazing opportunity for humanity to actually really, like you said, the singularity,
social singularity, and also physical singularity.
Yeah, exactly. We're like reaching a nexus, and I think we have this opportunity to, like, completely, for our world to like completely flourish.
It's exactly what I keep talking about in my talks as well. We have the chance to flourish in a beyond imaginable way.
Exactly, and I think most of the people of the earth are on that, on that vision, on that path. We just have to get the institution to come along with us,
not to destroy us.
Yeah, exactly. So that's important. But I think we're getting there. It's been scary for the institutions. In the past, I think a lot of this information was available. It just was not acceptable for certain reasons. Some of those reasons were good. During the First World War, Second World War, some of these discoveries were happening, including zero-point energy, and it might have not been the greatest idea to give
to some people
this kind of power.
I mean, I believe that Hitler was having research in different areas.
In this field, very specifically, very close to what we're talking about. And
good that it didn't go through.
Yeah, exactly. At the time of Nikola Tesla, you know, there was a lot. There was many inventors after that. It's just that the control of the information stayed when it could have been lifted. And I think now it's time where it gets lifted, you know, when it gets exposed. And when we put all this together, it as well, you know, changes the way you think of yourself, the way you think of yourself with the universe. Yeah, I'm in the middle of publishing an article, a paper on how the zero-point energy scales in the body, you know, through the water structure, like the carbon atom, the water structure, and then the microtubules, the microtubule bundles, and all this, to eventually produce the information that we call consciousness, you know, so that, like, we're not separate from the field neither, because we're made out of all these protons and stuff. And
so how does consciousness enter in? That's
and so then it really changes the way you see yourself relative to the universe. All of a sudden, you're not just like this little insignificant, random thing that happened by chance, that somehow, you know, the universe made humans, but that actually you're part of the evolution of creation, you know, and that you have a role to play in informing the field, you know, and the field is informing you and your reality. And so it changes really fundamentally. So then you realize that, oh, you know, everything I do has an impact on everything else. It's not me separate from the rest of the universe. It's me with the rest of the universe. And so then, you know, you think twice before you say, you do things or say things that are hurtful, you know, and so like, it has a really deep philosophical and social meaning to discover these things in physics that are just equations in physics, but they say something that like transforms internally people. And I think that's like really an amazing opportunity for humanity to like become harmonious. I mean, one of the biggest stressors that produce war is the idea that there's a lack of resources and lack of energy to get the resources. That like, but
we are already almost there to get the unlimited source of energy.
Exactly. And it's happening everywhere around us, and we can get there. There's been almost zero funding towards, you know, like we have nuclear fusion, nuclear fission, you know, all this billions of dollars going into these devices that have promised to produce power, but like tokamaks and so on that have not produced 1 watt of power. But actually throughout history, there's all these inventors that were able to just tickle the energy out of the fundamental field. And so this is like an opportunity. And then, so when that happens, then the stressors that produce war go away, right? Because you have almost infinite amount of energy anywhere you are in the universe. And if you have gravitational drives, you can go around the galaxy, whatever material you need, there's plenty. Right? There's no need to fight for material.
The material world is ending in a sense that material is not the value what we need to strive for.
Exactly. The value is the creativity.
The creativity, our
what you're doing with the material. Yeah.
Indeed.
Yeah.
This is fascinating.
It's remarkable.
But of course, this comes with a lot of difficulties. Like if suddenly we have unlimited source of energy, that what it means that some people may tend to degenerate, right? So we need to make sure that people have the energy, motivation to go beyond comfort zone, to train themselves, not to become lazy and
yeah, for sure. Yeah.
Addicted to.
But I think that, like, you know, this is something I really thought was really cool about COVID. Because I saw people, of course, a certain percentage of the population became couch potatoes. But most people not. Most people, I mean, maybe for the first few weeks, but then, you know, they start to say, oh man, I've always wanted to do this and I never got to do it. So let me do this, you know, and, you know, people became creative and like, you know, without the stressors that they had every day, you know, to like do the things and like transform. And like, I saw so much personal transformation during that time. So I think, I mean, of course it was a horrible situation, but there was a lot of positive in it too.
Yes.
And you know, I really enjoy seeing flowers starting to grow in the middle of highways, you know, because there was no traffic, you know, and things like that. You can see how fast the earth can recuperate when you change, you know, the way you're doing things.
Right.
And we could like totally do that. We could totally change. And it's really just one understanding how gravity works and where energy comes from. So maybe it's...
automatically we get rid of the pollution and all the troubles.
That's right. All kinds of problems we experience in, you know, like the challenges we have in nature, you know, like dealing with nature. Like, so, I mean, is this... like we have to open up.
Mm.
Science has to open up. Censorship has to stop. You know, basically, we have to say, okay, everybody has a voice, and like, let's discuss all of this. No idea is too crazy. Let's just see what's good, and what's not good is gonna go away. Like, we don't have to be afraid of new ideas and new concept and new discoveries. We can, like, you know, in a mature way, have conversations about it and grow all together. It's really powerful, and I think we're getting there finally.
Yeah.
I mean, so
the society is ready for this to embrace. There is obviously, we have this issue with some hatred, negativity, which may be deeply rooted, that might be a problem, but let's hope that the healing process that is enabled to us by having energy and having connection and being able to travel like that, let's hope that it will start to zero out even the hatred amongst people.
yeah,
there.
I mean, most people are so traumatized, you know, generational trauma from all the wars and everything. And so basically, we have to have the compassion, you know, when we look at what people are doing. Why are they doing these things? It doesn't come out of nowhere. No baby is born a natural killer, right? Babies are pure. They're born, but they, you know, there's trauma that occurs, and so we have to have that empathy, right, to be able to say, okay, well, what brought somebody to get into that place, and how can I bring them out of that place and show them the beauty instead of, you know, all the difficulties.
And we can now show the beauty of physics to people.
Yeah.
And the understanding of the interconnection, which goes directly against the separation that
exactly, against the I'm here, you're there,
and then I'm the right one, you are the evil one. That doesn't make sense at this point.
No, exactly. And you know, with this kind of energy capacity and gravity control, we'll be able to do things that are miraculous. Like, we can take a desert and greenify a desert.
Absolutely.
Right? We can desalinate water and give water to everybody. And, you know, we can take care of everybody, right? So that, like, we're one human race, right? And not like all these, like, we all have different cultural background. We should be encouraged.
And this is great, of
yes,
course.
It's great.
Because this is the richness, there's the creativity that we are offering. And by connecting with respect to the other cultures, we can expand even further.
Exactly.
Mutual support gives rise to yet another unexpected levels of creativity.
Exactly. And new ideas and new concepts and all this. And so, but at the end of the day, we're one race on one planet. That is our home, that, like, is feeding us, that is taking care of us, and we have to unify. You know, we do, and the physics that are emerging are physics that are showing that unity, that are, and so I'm really hopeful that it will encourage people to stop dwelling on the differences, and, you know, start realizing the common cause, the common relationships.
Yeah, and I believe the one thing that we also might need to focus on is the fears of people, mitigate fears, because all what I can see, the hatred and all the evilness, and it comes from fears.
Yeah.
I believe, and the physics shows it now, that we don't need to fear about our future, that we will have abundance in material world.
Yeah.
Let's think about what makes us happy.
Right.
We are happy when we create things, when we can discover new things, and everybody can do it now.
Yeah. And, you know, at the end of the day, like, understanding ourselves and the universe is really the highest level of,
Yeah.
you know.
It's the limit of what, for me, what I can imagine.
Right.
The limit of everything for
Yeah.
my brain
Yeah.
is understanding the universe, understanding society, what's happening,
Right.
and going further, deeper in the creation and understanding
And
our universe.
yeah, and understanding of ourselves, and it's. I mean, I can't see any other reason for life to, you know, to exist. Like, it really is the universe learning about itself
And
through us.
through us, and this is the reason why we are still going through all these terrible things, why we had to experience in the past the most catastrophic things in order for us to learn about ourselves.
Right.
And our consciousness goes into the fractal of the deepest negativity
Yes.
in order to see the fractal of the
highest
consciousness.
Yeah, for sure, because you don't learn to walk without falling.
Yeah.
You have to fall. You know, if that contrast wasn't there, then there would be nothing to strive for. They would, like, it would be really boring if you could create exactly what you want, like, instantaneously.
That's not interesting at all.
No, you would be bored for the rest of eternity.
But nevertheless, we are now coming to the point that we can almost create anything after this history or these all troubles.
Yeah.
Still in trouble.
Yeah.
We are getting to this level.
Right.
So what I believe is that once we cross this point of the social singularity, then we are almost in a point that we can create everything. But it's important to remember to be able to appreciate it, to not to fall into the darkness of normality. Things
Right.
are beautiful, things are just amazing,
Yeah.
and when we just get used to, oh, it's normal, it's not interesting. But
Right.
we need to see and appreciate the complexity and the beauty in.
Yeah. I mean, the good thing is that if it comes as well with gravitational drives and warp drives and all this, is that, I mean, there's so much to explore.
Yeah, that
there's
is true.
so much to admire and see. I mean, the beauty of the universe is incredible.
I'm sure that we will meet also other civilizations. There is no reason for us to be alone.
Exactly. There's no reason for us to be alone. There might be some really cool people out there we want to hang out with. And so there's really amazing, like, there's an infinite amount of things to discover.
Yes.
We're never going to run out.
It's unlimited.
Yes.
We are in a fractal existence.
Exactly. So it's an amazing thing. And you can actually see, like, if you do like a big brush pictures, you know, like from a really high stand, that, like, the evolution of consciousness is directly related to the evolution of how far we can go from our home. Right? Like, caveman, you know, couldn't go very far. Right?
Sure.
And then, like, we got a little further, you know, and then agriculture and all this. And then eventually we, you know, were able to, like, have point, horses to go, like, further, and then cars, you know, and then flights and all this, you know. And then it's like, this is the next step. You know, oh, you know, we can move away from the planet. Because as well, people don't realize planetary systems are not stable. They're not like, they don't just stay like this perfect for, like,
it won't be
ever.
Forever. Right?
Yeah. Eventually there's a comet that comes too close, so there's a sun flare, or something happens, and then the planet loses its atmosphere and it's over.
Yeah, so we must be able to move ourselves in the air.
Exactly. We have to be able to move, and we can't do it with rockets.
Yes, of course.
It's not going to happen with rockets. You can get, like, short distances with rockets, but you know, even the moon and Mars, which is really not far, you know, Mars is such. Like, it's not going to happen with rockets. You would have to launch thousands of rockets every time you have a window, which is every 2 years. You know, you get a window where you can launch rockets to Mars, and you would destroy the ionosphere, like the ozone layers. I mean, there's all kinds of issues with this approach. Like, really, we just have to understand how to use gravity, just like Maxwell and Faraday and all this give us information on how to use electromagnetic field, and we got this whole technology out of it, right? The next step is to figure out how to use gravity, not just electromagnetic field, and these equations show there's a direct relationship between the two.
So let's hope, let's make all what we can for that our next chapter of evolution is on the galactic level.
Yeah, totally.
And then when we can see about with this universe within universe, the next can be our universe level, and then can be the another
the multiverse
level, and we are here for
and then it's gonna be epic. I mean, you know, we gotta get past the speed of light, but you know, it might be a little bit later on. But already going around the solar system would be amazing.
It's amazing.
Yeah,
and we already do have the physics for that. It's not magic anymore, but it is within the structure of how we understand our universe.
Our physics. Yeah, it's just little tweak of physics that was already there, and then you put it together, and then all of a sudden you get the key, right? And then you know, people say, but how is it going to work? Not everybody's going to have their own spaceship in their backyard, you know, from the start. But instead of getting into a plane, you might get into a vessel, right, that is piloted by competent pilots, right, that is going to bring you, you know, to Jupiter or Mars or
vacation.
Jupiter, yeah, exactly.
Looking from the universe.
Right.
It's such a dream.
Exactly. And then at the same time, then that gives us the capacity, the technology, like if there's a meteorite that's coming towards the Earth, if there's a comet, whatever, then we can deal with that if we have gravity control. If we don't, then it's a big problem. Yeah, so we have a limited amount of time to get the job done. And we're right there at this moment. It's like a really important moment in human evolution. Yeah.
So important.
Yeah.
Thank you so much for this great, amazing, enlightening meeting.
Oh, thank you.
And please, maybe you can tell the viewers where they can find more information.
Yeah, so we're at spacefed.com. It's the International Space Federation, so spacefed.com, and you can go to our website where we're actually updating the website to an amazing portal for people to like come and hang out with us and participate and connect with us. There is I'm in the middle of, you know, getting some material out for laymen, for everybody out there, and so it should be out very soon. I'm very excited. You know, there's all kinds of ways you can get involved and support us in this research, because we're not, you know, supported necessarily by governments or, you know, special interests. So like you can get involved and discuss with us, and if you're a scientist, you can come and help us write physics. You know, we need a lot of help. And so, you know, you can connect to us at spacefed.com. Fantastic. It was so great to meet you.
I'm thrilled.
Yeah, we'll have to do it again one time.
Yeah, we will.
Yeah. Thank you.
Thank you.